one of our previous lectures, we have seen how DC shunt generators can be connected in parallel to supply a common load. A similar arrangement is sometimes possible with motors also, particularly with series motors. It is possible to mechanically couple two series motors to drive a common shaft, usually through a gear reduction. They drive the same shaft whereas the load torque is applied on the common shaft. This is N1 is to 1 and this is N2 is to 1. Normally, for series motor, these two machines are also electrically connected in series and connected across a supply voltage V t. It is possible to adjust the loading of the motors by properly selecting the gear ratio. Let us try to see how this is done through an example. Consider two identical DC series motors for which this V t equal to 250 volts. Both of them are rated at 20 horsepower and N equal full load, that is full load equal to 1000 RPM. The gear ratio are N1 equal to 5 and N2 equal to 4. The total load torque TL equal to 810 Newton meter. If the losses are neglected, P loss in both the motors are almost negligible. So, we have to find out what is the speed of this common shaft N, what will be the voltage across individual motors V1 and V2, and what will be the common armature current IA in such an arrangement. We also assume that phi f is proportional to IA, that is the machines are unsaturated. Now, for this particular case, N1 by N equal to 5 and N2 by N equal to 4. Therefore, N1 by N2 equal to 5 by 4. Since IA1 equal to IA2 equal to IA and phi f is proportional to IA, we have phi f1 equal to phi f2 equal to phi f. Therefore, E1 by E2, the induced voltages, equal to phi f1 N1 divided by phi f2 N2, but these are same as phi f. So, this is equal to N1 by into equal to 5 by 4. But since R A plus R E plus R A C is approximately 0, then E 1 plus E 2 equal to V T equal to 250 volts. Therefore, E 2 into 1 plus E 1 by E 2 equal to 250 volts. But we already have E 1 by E 2 equal to 5 by 4. This gives you the value of E 2 equal to 111 volts and E 1 equal to 139 volts. The voltage is V 2 equal to V 1 equal to E 1 because the resistance drop is negligible. Now, let us look at the torque generated. T E 1 equal to K phi F 1 I A 1 and T E 2 equal to K 2 phi F 2 I A 2, but these are identical machines. So, K 1 equal to K 2, also phi F is proportional to I A and I A 1 equal to I A 2, and since phi F 1 equal to phi F 2, therefore, T E 1 equal to T E 2. So, both the machines they share the torque equally. Now, let us look at the mechanical arrangement. The gear ratio is N 1 is to N. So, 5 is to 1. So, if the generated torque by the motor is T E 1, then the shaft torque contribution by motor 1 is 5 times T E 1 plus 4 times T E 2, which is equal to 9 times T E. This is the total shaft torque, which is given as 810 Newton meter. So, T E 1 equal to T E 2 equal to T E, this comes to 90 Newton meter. Now, what about the rated torque of the machines? T E rated can be found out from the rating of the machines, which are given as 20 horsepower. So many watts divided by their rated speed. 1000 RPM by 60 is the rated RPS into 2 pi the rated omega. This comes to 142.47 Newton meter. What about IA rated? Again, losses are negligible. So, this is the output power of the motors by the input voltage. This comes to 59.68 amperes. Now, we know in unsaturated DC machine T E is proportional to I A square. Therefore, I A in this case will be square root 90 divided by 142.47 into rated current. This comes to 47.43 amperes. Now, coming to the shaft speed, since losses are negligible, E 1 plus E 2 into I A, this should be equal to T L omega L. So, omega L equal to E1 plus 250 into 47.43 by 810, and N L equal to 60 into 2 pi. This comes to approximately equal to 140 RPM. So far, we have seen two types of DC series motor. One is the shunt motor, whose torque speed characteristics is a straight line with a little droop. This is the shunt motor. And the series motor, in which case the power drops very fast as the speed increases. In fact, for the series motor we know T E into omega plus R A plus R A C divided by K K F whole square equal to V T square by K K F. Therefore, T E omega equal to omega by plus R A C by K K F whole square into V T square by K K F. So, as the speed increases, the power output this drops. On the other hand, for the shunt motor, as the torque increases, power output also increases. It may be desirable to get a characteristic which is somewhat in between the two. The one disadvantage of DC series motor is that its no load, it does not have a finite no load speed. As the load reduces, the load torque reduces, the speed can become dangerously high, which is an undesirable feature. But one desirable feature of this is that as the load on the motor is increased, its speed drastically falls, thereby shedding a lot of power. Limit is more or less power limited. So, in order to combine these two features, that is, in order to have a definite no load speed, but a more drooping characteristics than the shunt motor, one can use a compound DC motor by adding a shunt field to a series machine as shown below. Normally, a long shunt cumulative connection is used, that is, it is a series motor to which a shunt field is also added. Of course, one can also see it as a shunt motor to which a series field has been added, but this can give interesting torque speed and all other characteristics. So, let us say this is the armature current I A. For this machine, we would write V t equal to the back EMF E plus I a into R a plus R s, where E equal to k phi omega. Normally, this phi m will be some nonlinear function of the shunt field current and the series field current, but if we assume the motor magnetic circuit to be unsaturated, we can write this phi m to be some k f into I f plus the equivalent field amperes of the armature current, which is N s I a by N f. N s I a is the ampere turns due to the series field, and the equivalent field current is that divided by equivalent field ampere turns is that divided by N f. If we replace this, then we get E equal to some k f into I f plus N s by N f I a into omega. In other words, we can write omega equal to E divided by where E itself is V t minus R a plus R s into I a divided by k f I f plus N s by N f I a, from where we can find out the current speed characteristics of the machine as follows. So, this can be written as omega into I f plus N s by N f I a equal to V t by k f minus R a plus R s by k f I a. In other words, omega I f plus N s by N f omega I a equal to V t by k f minus R a plus R s divided by k f I a. Rearranging, we can write omega I a plus N f I f by N s omega plus N f by N s into R A plus R S divided by K K F I A equal to N F by N S into V T divided by K K F. This can further be written as omega plus N F by N S into R A plus R S divided by K K F into I A plus N F I F by N S equal to N F by N S V T by K K F plus N F by N S whole square R A plus R S divided by K K F I F. This is equal to N F by N S into 1 by K K F into V T plus R A plus R S N F I F by N S. So, this is the current speed characteristics of the compound, cumulatively compound long shunt DC series motor. Please note that on the right hand side, for constant terminal voltage and constant values of I F, the right hand side is constant. So, this is again the equation of a rectangular hyperbola, but not with omega or I axis as the asymptotes now. The asymptotes are slightly different. So, this is omega, this is I A. These asymptotes are somewhat different. The interesting point to note is that at no load, that is at armature current equal to 0, the omega does not become infinity here. In fact, we can find out what will be this no load speed, that is omega 0 at I A equal to 0 from the given torque speed equation. By setting I A equal to 0 in this equation, we get N F I F by N S into omega 0 plus N F by N S R A plus R S divided by K K F this should be equal to NF by NS into 1 by KKF VT plus RA plus RS into NF IF by NS, or in other words we can write omega 0 plus NF by NS into RA plus RS divided by KF equal to VT by KKF IF plus RA plus RS NF IF divided by NS into KKF IF. This comes to VT by KKF IF plus NF by NS to RA plus RS divided by KKF, or omega 0 comes to VT divided by KKF IF equal to VT divided by K phi, just as the shunt motor with just the shunt field winding. This is expected. Now, let us look at the torque speed characteristics or torque current characteristics first for this machine. The torque of this machine is given by, just as any other DC machine, it would be K phi m I a, but phi m itself equal to K f into I f plus N s I a by N f Therefore, T e equal to K K f into I f plus N s I a by N f into I a. In other words, this can be written as K K f N s by N f into I a plus N f I f by N s into I a. But we have seen that so this is equal to kf in S by Nf into Ia square plus Nf If by Ns Ia. This can be written as Nf If by 2 Ns whole square minus Nf If by 2 Ns whole square equal to kf Ns by Nf into Ia plus Nf If by 2 Ns whole square minus kf Ns by Nf into Nf square If square by 4 Ns square or Te plus kf Nf If square divided by 4 Ns equal to kf Ns by Nf into whole square. Or so this is also the equation of a parabola, but not with the normal axis of Te and Ia, rather here also the torque current characteristics is given by this equation. am sorry, T E plus K K F N F. You can write this as K F I F N F I F divided by 4 N S. This is equal to K K F N S by N F I A plus N F I F by 2 N S whole square. So, this gives you a torque speed characteristic somewhat like this. This point is minus K K F I F N F I F by 4 N S, and this point is N F I F by 2 N S. Looks somewhat like this. We can also find out the torque speed characteristics by simply substituting the value of current. We have seen T E to be equal to K K F I F plus N S I A by N F into I A, and we have also seen from the current speed characteristics omega plus N F by N S R A plus R S divided by K K F into I A plus N F I F by N S equal to N F by N S K K F into V T plus R A plus R S N F I F by N S. From this we can write T E equal to K K F N S by N F I A plus N F I F by N S into I A. From here we can find out I A plus N F I F by N S to be equal to N F divided by N S K K F into V T plus R A plus R S N F I F by N S divided by omega plus Nf by Ns Ra plus Rs by Kf. Now, this value of Ia plus Nf If by Ns can be substituted in the torque equation as well as the value of I to get the torque speed characteristics, and the torque speed characteristics for this machine comes somewhat like this. Looks somewhat in between the DC shunt and the DC series motor, whereas for the series motor the torque speed characteristics would have been somewhat like this, and for the shunt motor it would have been this. This is shunt, this is series, and this is compound. Similarly, we can find out the other characteristics, for example, the speed current characteristics. RPM, whereas for the shunt it is again straight line, and for the series this is rectangular hyperbola. For compound it is also a rectangular hyperbola, but not with these two as asymptotes. So, this looks somewhat like this. So, this is shunt, this is series, and this is compound. It should be understood that we are talking about cumulatively compound motors. The torque speed characteristics for shunt we know it is a straight line. For series this is the series. For cumulatively compound we will get something in between. This will be shunt, this is series, this is compound. The interesting thing is these characteristics of shunt and series machines, the compound machine can be controlled by controlling the proportion of the series or shunt field ampere turns as a percentage of the total ampere turns of the machine. Let us look at it through an example. Let us consider a cumulatively compound DC motor. The characteristics is its starting torque equal to 140% of the full load torque, while the starting current is 130% of the full load current. The full load armature drop is 12% of the rated voltage, whereas no load armature drop is just 2% of the rated voltage. For this, we have to find out what is the shunt ampere turns as percentage of net ampere turns at full load. We have to find out what is the percentage of shunt ampere turns as the percentage of the total ampere turns at full load, and also what is the no load as percentage of full load. For these characteristics, we have to find out how much shunt ampere turns will be necessary and what no load speed will it give as a percentage of the full load speed. To solve this problem, we note that T start equal to K K F into I F plus N S by N F I A start into I A start. This can be written as K K F I A start into N F I F plus N S I A start divided by N F. Similarly, full load equal to K K F I F I A full load into N F I F plus N S I A full load divided by N F I F. Now, if we divide, then T starting by T full load, which is 1.4, this comes to N F I F plus N S I A at starting divided by N F I F plus N S I A at full load. This is equal to 1 plus N S I A at starting minus I A at full load divided by N F I F plus N S I A at full load. This into I A start divided by I A full load into I A start divided by I A full load. Now, this again is 1.3, therefore, we have 1.4 divided by 1.3 equal to 1 plus Ns IA start minus IA full load divided by NF IF plus NS IA full load equal to one plus NS IA full load into IA start by IA full load minus 1 divided by NF IF plus NS IA FL. Therefore, 14 by 13 minus 1 equal to NS I FL IA FL divided by NF IF plus NS IA FL into this thing is known as 1.3 minus 1. Therefore, NS IA FL divided by NF IF plus NS IA FL equal to 1 by 13 into 1 by 0.3 equal to 10 by 39. Therefore, the field ampere turns NF IF divided by NF IF plus NS IAFL as a percentage of net ampere turns equal to 1 minus 10 divided by 39 comes to 29 by 39, which is 74%. And to find out no load speed, we note that IA RA plus RAC at full load equal to 0.12 pu, IA RA plus RAC at no load equal to 0.02 pu. So, E at full load equal to 0.88 pu, E at no load equal to 0.98 pu, phi at no load divided by phi at full load equal to NF IF plus NS I a no load divided by IF plus NA IA full load. This is equal to 0.74 plus NA IA full load divided by NA IF plus IA full load into IA no load divided by IA full load. This comes to 0.7833 and E no load divided by E FL equal to phi no load into N no load divided by phi full load into N full load. Therefore, N no load divided by N full load equal to phi full load divided by phi no load into E no load divided by E full load. This comes to 1 by 0.7833 into 0.98 divided by 0.88. This is 142%. Thank you.